Yeah, we can start. Yeah, we can start. Dr. Kalpana, you are muted.
Now it's audible, ma'am?
Yeah, please start.
Okay. Good afternoon to one and all present here in the forum. I, Dr. Kalpana Patel, on behalf of Department of Physics at SRM Institute of Science and Technology, Delhi NCR campus, welcome you all in this lecture jointly organized by Indian Physics Association, Department of Atomic Energy, Board of Research in Nuclear Science, and SRM IST. I heartily welcome today's speaker, Professor Anuradha Mishra from University of Mumbai, Professor Vanna Nanal from Tata Institute of Fundamental Research, and also the General Secretary of IPA, Professor Samit K. Mandal from University of Delhi and Joint Secretary of IPA. I also welcome joyfully our Dean Campus of Life and Head of BTech First Year, Professor Naveen Alavat Sir, Dean of Academics, Professor D.K. Sharma, and our Deputy Registrar Sir, Professor S. Viswanathan. Now, I would like to request Professor Samit K. Mandal to give some information about IPA and Raman lecture to the audience. Thank you. Sir, please.
Thank you, Dr. Kalpana Patel. This is the one of the North India lectures in the North India. We are doing the lecture series, and we are thankful to the SRM Institute that they are agreed to host this lecture, this Raman lecture. And before the starting the lecture, I just talk few words about the IPA. So maybe I just try to share my screen. I think it's visible, hopefully.
Yes.
Thank you all. Indian Physics Association, it was started, I think, in 1970. So already we have more than 50 years, it's 51 years after founding the Indian Physics Association. At present, the Indian Physics Association, the website is hosting at the TFR site. And this is you can see the two address, the Gmail address. So if you want to any communication, so you can connect to us directly. And this and also you are in the YouTube as well as the Twitter and also in the Facebook. So we generally post every functions. That means like the hosting the lecture series or any other like award ceremony, everything we generally post in our website as well as in the Facebook and also in the Twitter. So in IPA, we have at present we have 47 chapters and around 4,400 members, a little bit more than 4,400 members. And our chapters are distributed all over the India. So you can see from the left side of the map. So all 47 chapters are distributed from the north to south, east to the west of in India. And our main activity is mainly the interaction. So it's a platform for interaction with the scientific minds. And the last 50 years, we are continuously doing this activity, and Some of the except this interaction, we have also organized the lecture series, and also we have a few awards. Maybe I'll mention what are the awards are there, and those are awards generally will given the every two years. And we are also have a the present in the international, so we have a several MOU with a different the society all over the world, like a American Physics Society, then Institute of Physics UK, then the Italian Society for Physical Society, and then also we are the member of the Association for the Asian Pacific Physical Society, AAPS, and the activity what we mentioned right now. So except that we have recently, I think 3 years, 2017, we have also introduced the special the chapter in our, or the special group in our IPA, that is the gender group. So maybe I'll talk a little bit later. And then here you can see the several, we have also the, we are also published few journals. Some of the journals are at presently every 3 months we are publishing the journals, and some of them are hard copy, but presently we are thinking we can go into the soft mode. So also several of the soft copies are available in our websites. And the awards which we are right now we know from the IPA side we are offering, that is mainly from the physics student, physics scientist. Some of them are for the older, I miss little bit the seniors faculty. Some of them are for the mid faculties, and some of them are the junior faculty. And recently we have also introduced few new the awards. And some of the also awards are mainly for the PhD student, like the CBK Baba Award or CL Bhatt Memorial Award. Anil Kumar and Anil Kumar Award. This is mainly for the PhD thesis award, and the Rahul Bose Memorial Award mainly for the high energy, and CBK Baba is mainly for the nuclear physics, and Anil Kumar mainly for the solid state physics. And also we are linked with the Indian Astronomy Olympiad and also International Physics Olympiad. At present, the office bearers are all leading by the Professor Ramakrishnan from the TFR, and Professor Tanushree, who is right now, she is the Vice President, and Professor Bandana Nala is the General Secretary, and myself is the Joint Secretary position, and Dr. Anuradha Srivastava, Aradhana Srivastava, she is working, she is presently act as a treasurer. And as I mentioned that we have 2017 onwards, so we introduce this new, you can say the group or chapter. This is a gender in the physics working group, and there is some member of this group at the present moment. And the founder member or the founder, the chairperson is the Prajal Sastry. Right now she is also the member of this, she has the past the chair of this group. And this particular group is right now working is in a different dimension, you can say, and quite important for the IPA, the work IPA. And you can join our IPA, so you can join directly through the website. And recently we introduced, and thanks for that. All the effort is taken by the by TFR group, leading by Professor Bandana Nanal. So you can directly join our the IPA, Indian Physics Association, and there is the address are mentioned here. So the tfr.race.in and the IPA 1970 and the IPA. This is the address where you can go directly from your web page. And some of the recently some of the lecture series we have organized in the different part of the country. Is mentioned, the different speakers are mentioned here. With that, I think I should also. thanks the SRM for hosting the this lecture series, the Raman lecture series. Okay, I just hand over the mic to Dr. Kalpana. Okay, thank you.
Thank you, sir. Now, audience, SRM IST Delhi NCR campus was founded in 1997, and it has more than 5,000 learners practicing their career in different fields. It also delivers graduate, postgraduate, and doctoral curriculums. Apart from this, many proficient degree level courses in engineering and technology, management, computer applications, pharmacy, and hotel management are also provided to the students. The SRM Institute of Science and Technology accreditations and rankings are as follows. It is AICTE approved, UGC awarded as Category 1, NIRF ranking as 35th, and NAC ranking A++. And it has also achieved MHRD ranking as A+, and ARIIA by MHRD as second rank. Department of Physics at SRM IST Delhi feels proud to have Professor Anuradha Misra as our speaker, with title of the talk as Quantum Chromodynamics at 50, a glimpse into the colorful world of quarks and gluons. Professor Anuradha Misra has done MSc from IIT Kanpur, PhD from IIT Kanpur, and her research area is from theoretical high energy physics and has specialization in quantum chromodynamics, light, front field theories, and spin physics. She worked at University of Mumbai, Department of Physics from 1995 to 2021 as assistant associate and professor, and superannuated in November 2021 as senior professor. Presently, she is a visiting professor at University of Mumbai, Department of Atomic Energy, Center of Excellence in Basic Sciences. She is also a senior associate at International Center for Theoretical Physics, Trieste, Italy, and fellow of National Academy of Sciences, India at Allahabad. So this was a short introduction of SRM with a short introduction of our guest speaker also. Now, I would like our speaker to please give us a knowledgeable talk on quantum chromodynamics at 50. Ma'am, you are heartily welcome from Delhi campus of SRM IST, and I would like to give the forum to you now. Thank you. Ma'am, please.
Should I share my screen?
Yes, please.
Okay. First of all, thank you very much, Dr. Vandana Nanal and IPA for giving me this opportunity. I am honored to be invited to deliver this IPA DAE CV Raman lecture. Thank you, Dr. Kalpana and SRM Institute colleagues for hosting the talk. I must start with an apology to the experts in the audience that although the title looks very, very technical, it is going to be a very elementary talk. I target the audience at SRM Institute. I understand there are a lot of engineering students, so I would like to keep the technical stuff to the minimum and say my story with words and pictures. So the title of the talk is QCD at 50, a glimpse into the colorful world of quarks and gluon. Before starting, let me just explain for the benefit of students what is the meaning of all these fancy words in the title. So quantum chromodynamics is a theory of strong nuclear force. It was proposed in 1972, hence at 50, it is completing 50 years this year. The theory was the culmination of efforts of a wide community of particle physicists to understand the structure of particles like protons and neutrons. And it is a very important component of the current theory of particle physics, which is called a standard model. And this theory, standard model, describes how the most fundamental objects in nature interact with one another. So in this 50th year of the birth of QCD, we are going to revisit the journey of particle physics from protons to the quarks and gluons, and how the theory called QCD was born. So I'm not going to, although the title says at 50, I'm not going to talk much about what happened after it was born in the last 50 years, but rather the story of the previous 20 years over which 15 or 20 years over which the developments took place, which gave birth to the idea of quarks and gluons and quantum chromodynamics. So the plan of the talk is as follows. I will first introduce what is standard model, what do we do in particle physics, and then I'll talk about the main part of my talk is the story of how we arrived from the picture of protons as the elementary particles to the quarks and gluons being the fundamental constituents. And this was expressed in terms of what is called quark model now, how the quark model was born, and then from there how the quantum theory, that is quantum chromodynamics, was born. And finally, I'll talk very briefly about why we still need to talk about QCD, even though it is already 50 years old, and then I'll summarize my talk. So to begin with particle physics, I hope everybody is familiar with what is particle physics. This is a quote from Baryon, and it says that it is the unbelievable in the pursuit of unimaginable. And we try to pinpoint the smallest fragments of the universe. So we are, the particle physicists are trying to look for the smallest constituents of matter. And for that purpose, in the labs, they had to build the biggest machine in the world. So the questions that we, the particle physicists, ask are the same which have been asked by people for over the centuries. That is, what are the ultimate components of matter, and how do they come together and form the matter? So the answers of these questions will require identifying what are the components of matter, what are the forces that govern their behavior. And the job of theoretical particle physicists like me is to look for a mathematical framework which will describe how these constituents come together and form the matter, how they interact with each other, and then from whatever theory we construct, we try to predict their behavior under different conditions. And then it is the job of the experimental particle physics to go and check in the lab whether our predictions are wrong or right, because that will decide how good or bad my theory is. So the earliest answer to this question, everybody knows, was in terms of the 4 elements or 5 elements in Indian philosophy, Panchatattva, Greek philosophy, 4 elements. And since then, the definition of what is elementary has been evolving with time. So I'll directly jump to what is the current answer. The current picture is that is the world is made up of elementary particles of 2 kinds. The particles here in the outermost ring here, can you see the cursor? Hello?
No. Yeah, now we can see.
Okay. So the particles in the outermost circle here in the red and green are what are called the matter particles. So there are the ones in red are what are called quarks, and there are 6 types of them. They are called up, charm, top, down, strange, and bottom. And what we have written here are the short names. The ones in the green are particles like electrons and neutrinos, and they are also 6 in number. In the middle ring, that is in blue, the particles are called the force particles or the intermediate particles. These are the particles which are responsible for force exchange between the matter particles, which are in the outer layer. And again, there are 4 kinds of them. Photon, that is gamma, is the mediator of electromagnetic force, usual electric and magnetic force that we know of. The one which is called G is the force particle of strong interaction, and this is going to be one of the main characters of our story today. And W and Z are the mediators of what is called the weak force, which is responsible for radioactivity. So we'll come back to these ideas again. These are the four fundamental forces. We have the electromagnetic force, which keeps the electrons bound to the atom, to the nucleus in the atom. We have the weak force, which is responsible for radioactivity and also for energy generation in sun. Then we have the strong force, which is the topic of today's talk. This is the nuclear force, which keeps the protons and neutrons together in the nucleus. And then finally, we have the gravitational force, which everybody is familiar with. The standard model of particle physics does not talk about the gravitational force. So what is fundamental is a question that depends on our knowledge of the science and also the technology. So what was fundamental 100 years back is not fundamental anymore. In 19th century, people thought that atom was the most fundamental object. That is the definition, that is the literal meaning of the word atom, that one which cannot be destroyed, broken up. But then people realized that atom is made up of nucleus and atoms and electrons, and nucleus was supposed to be the basic entity. And then finally, people found that nucleus is also made up of protons and neutrons. Now we know that protons and neutrons are also made up of smaller constituents, which are called quarks and antiquarks. And you can see the word scale written here, which says that, which gives the size of the system. So as the time evolved, one was able to look at the structure in finer and finer details, which means one could go to the smaller and smaller distances. So the what was particle physics at 100 years back is now not particle physics anymore. So this definition changes, and it changes with the advance in technology also, because if we have machines which can go deeper into the matter, then only we can see the structure. So 100 years ago, we did not have the technology to look to break a proton or to look inside the proton, and that is why the proton was considered an elementary particle. This is a picture which gives you an idea of what are the scales that are involved in different branches of science. So you can have length scales of the order of 10 to the power 19 to 22 meters if you are working in astronomy and astrophysics. This is the one in the center where you see 2 Newmans is the scale of the order of 1 meter, which you see in your everyday mechanics problems. On the other side of the center, you go to the smaller and smaller distances. So as you go to smaller and smaller distances, you are able to see the bacteria and then DNA, you're able to see the molecules, atom, and then inside the atom, the nucleus, and the smallest scale that we can see right now is inside the proton, that is the quarks and antiquarks. So high particle physics, which is also called high energy physics, looks at the matter at the most, at the smallest scale. And this is how, this is a picture, I've taken a lot of pictures from the internet. This is another picture which explains how do you see objects at different length scales. So at very large distances, in astrophysical and astronomical distances, you use large radio telescopes and telescopes. For ordinary everyday physics problems, you use your eye. You can just measure things with a scale and look, your eye is your instrument. When you go to smaller distances, 10 to the power minus 4 meter or so, you need a microscope to look at objects involved in that area. Even in smaller distances, you need electron microscopes, which is the region of atomic physics. And then when you go to nuclear and particle physics, the instruments with which you see the system are your particle accelerators. So how do we see objects at the smallest scales? We use very huge machines, which are called accelerators. These accelerators accelerate particles to very high energies. And after they are accelerated to very high energies, they are made to collide at certain point. And then at that point, when the collision takes place, some new objects or new particles are created and they come out. And the scientists build detectors around these points and try to identify the signals that they receive in the signal to figure out what particles were created, what kind of interaction has taken place. So this picture at the bottom, on the left, is the picture of the Large Hadron Collider at CERN in Geneva. Many of you must have heard about it. This is the place where the famous Higgs boson was observed, experimentally seen first time. So this huge large ring contains two counter-rotating beams of protons. They are accelerated to very high energy. They are about to collide. And then around this circumference of this whole thing is underground, and it crosses two countries. It is huge, 37 kilometers in perimeter. So there are 4 points around the perimeter where you put your detectors, and when the protons collide, they create new particles, and then these all the data from the detectors is sent to huge computers, and there are a lot of scientists which are involved in analysis of what is the data collected there. So this is a way to see the elementary particles in particle physics. So basically, this seeing involves a whole lot of people. So there are 3 sets of people who are part of this exercise of observing or detecting new particles. They are the experimentalists. The experimentalist job is to set up an experiment like the one I just described and take observations and then try to interpret the data there. And here I have a picture of the Rutherford scattering experiment, a prototype of an experiment, any high energy experiment now. Then there are theoreticians like me who mainly work with paper and pen and computers, and they try to find some mathematical laws which will explain these physical phenomena which are taking place in the lab or in nature. And then there are phenomenologists who take inputs from the experimental observations, who take inputs from the theory and try to build models which will explain the data. And then they also make predictions on the basis of their models, which again are taken to the experimentalists who try to check the models by again planning experiments which will test the new predictions. So this is the way in general things proceed in physics. And here I have a picture of a grid computing, because these days in high energy physics, the experiments involve so many people, hundreds of institutions and thousands of physicists, and the data that is, for example, taken at LHC is put into large computers, and then people sitting in their own countries using grid computing are able to analyze this data and get results. So the journey of particle physics has been a very nice story of this give and take between theory and the experiments. And you can say that this journey started with the discovery of electrons, which was considered to be an elementary particle in 1897, and it is considered to be an elementary particle even now after 125 years, 125 years. So at that time, in the beginning, the atom was considered to be the elementary particle, and then there was a picture of the atom given by the plum pudding model, according to which the atom is a ball of positive charge, and there are negative charges called electrons embedded in between. This picture was changed with the discovery of nucleus by the Rutherford experiment. So Rutherford did this experiment in which he bombarded a gold foil with alpha particles. Here you can see that there is a gold foil in the middle and alpha particles are hitting it. And then he put a detecting screen around it, and he counted the number of scattered particles at different angles and different energies. And this is what we do in all high energy physics experiments even now. We look for the spectrum of scattered particles. This quantity is called scattering cross section. The quantity that we measure is called scattering cross section, which is measured in the lab and which can be calculated by a good theory. So one looks at the distribution of scattered particles and tries to find out what kind of scatterer is there. So if the plum pudding model was correct, then most of these particles should have gone undeflected. As you see in the upper picture here, Thomson's model says that most of the particles go undeflected. Some of them may get deviated a little bit from their path. But what Rutherford observed was that some of the particles even back scattered. And that indicated the presence of a hard, heavy target in the middle. And that brought in the concept of the nucleus. The result of Rutherford scattering experiment suggested that there is a all the positive charges contained in the center of the atom, and the electrons are moving around it. So this lightest nucleus of the hydrogen atom was called the proton. And the next question that arose was, why is the helium atom 4 times as heavy as the hydrogen atom, while it has only 2 electrons? Because atoms are neutral, so if it has 2 electrons, it should have 2 protons also, and therefore it should be twice as heavy as the hydrogen atom, but it was actually 4 times as heavy. The same thing about lithium. It should have been thrice as heavy as hydrogen atom, but it was 7 times heavy. And that, which meant that there was something which was neutral, which did not carry a charge, that was also present in the nucleus, and that thing was called neutron. And the prediction of neutron was confirmed by James Chadwick in 1932. And this is an experiment in which he bombarded beryllium target with alpha particles, and he concluded that there are neutral constituents present inside the nucleus. So that gave this picture of the nucleus, which is made up of neutrons and protons. And they are tightly packed because nucleus is very dense, as we saw under the scattering experiment. Now, a heavy nucleus will have a lot of protons and neutrons packed in a small space. And how is that possible? Because protons are all positively charged. Neutrons don't have any charge. So they should repel each other and they should just come out of it. How do they form a stable system? So their being together in the nucleus meant that there is some other force other than the repulsive electric force, which is keeping them together. And this was called the nuclear force. So the nuclear force was explained by Yukawa. He gave a theory in 1935 in which he said that the nuclear force between the nucleons take place because of exchange of a certain particle, which he called meson. Now, this idea of the force being mediated by an intermediate particle was not new. So if you look at electromagnetic force, the most familiar force for us, we have all done electricity and magnetism in our high school. So the electromagnetic force between charged particles takes place, was considered to be taking place through a field, okay, an electromagnetic field. So the like charges repel each other, opposite charges attract. And Maxwell gave a theory which explained this attraction and repulsion in terms of an electromagnetic field, which is created by one of the charged particles, and because of which the other charged particle feels the force. This was the classical picture of electromagnetic force. And all the laws of electrodynamics were contained in what are called Maxwell's equations, which you must be familiar with. And this is the foundation of what the subject called classical electrodynamics. Now, classical electrodynamics is a classical theory. A classical physics theory is a theory which describes the physical world at macroscopic distances, that is, usual distances that we deal with in everyday life, and ordinary velocities that we see in everyday life. At the beginning of the last century, that is 20th century, 2 landmark ideas emerged in physics which changed everything. These 2 ideas were the ideas of relativity and quantum hypothesis. So the relativity idea says that the laws of physics, which are valid at ordinary velocities, are not sufficient if the objects which we are looking at are moving with velocity of light, and you have to change your laws of physics to satisfy the requirement of relative Lorentz covariance. So for the physics students, this was the shift from the Galilean transformations to Lorentz transformations as the fundamental transformations when you go from one frame to another frame. The quantum hypothesis was said that the laws of physics, as we know them in classical mechanics, are not sufficient if you go to very small distances, and you have to use the rules of quantum mechanics. These 2 subjects were developed about 100 years back, and all our physics is now based on these ideas. So the Maxwell's equations, which were describing the electromagnetic force, were consistent with the theory of relativity to begin with, right from the beginning. However, when you go to small distances, that is at microscopic scales, then the laws of electrodynamics needed modification according to the rules of quantum physics. And that led to the idea of need for a quantum theory of electrodynamics, which is called QED, or quantum electrodynamics. in very loose terms, the basic idea in QED is that the force between two charged particles takes place through the exchange of the quantum of electromagnetic field, which becomes a particle. So instead of the force being mediated by an electromagnetic field, the force is mediated through the exchange of a particle, which was called photon. We are all familiar with how the photon was introduced by Planck to explain the black body radiation. And then the idea was taken over by Einstein to explain the photoelectric effect. And basically it says that light comes in small packets, which are called the quantum of the electromagnetic radiation, and they are called the photons. The concept of photon was further verified by Compton in explaining the Compton effect, which describes the scattering of light with electrons. And what he concluded was that it can be explained if we consider light to be made up of particles, massless particles, and these were the photons. So this was the first example of interactions being mediated by exchange particles. Why I'm talking about so much about electrodynamics? Because we will see that quantum chromodynamics is very similar to quantum electrodynamics in many ways. And this is one of the key ideas in all the theories of all the forces, that the forces are to be mediated by exchange of a certain particle. So here I have on the screen pictures which are called Finemen diagrams, which represent pictorially physical processes in terms of diagrams. For example, the middle one has two electrons interacting, exchanging a photon and scattering. So the lower ones are incoming electrons, they exchange a photon and then they scatter. So the middle picture describes electron-electron scattering through exchange of a photon. The same idea is behind all the three theories. In the lower picture, we have the weak interaction, where the weak force between quarks and electron and neutrino is mediated by what is called a W particle. And in the top picture, we have two quarks, a green quark and a blue quark, interacting by exchanging a photon. So the four fundamental interactions. So we have four fundamental interactions as we have seen, and they differ in various ways. They differ in their relative strength, in range, and in their nature, whether attractive or repulsive. And also each one of them has their own mediating particle, which is called the intermediate vector boson. So the next particle, photon was, so we had the electron, we had the proton, neutron, and we had the photon. And the next particle that was discovered was a positron. Now positron was again a prediction of theory. So Dirac built up a theory of quantum electrodynamics in 1927, and this theory required that there should be a particle just like electron, except that its charge will be opposite to the charge of electron. This was called the antiparticle of electron, and it was given the name positron, and it was found by Anderson in a cloud chamber experiment in 1931. So the list of elementary particles by 1932 was, we had the electrons, proton, neutron, and photon as elementary particles. We had the positron, that is the antiparticle of electron, which was rejected also. We had the proposed meson by Yukawa, which was supposed to be the mediator of weak force, of a strong force. And then there was another particle called neutrino, which was needed to explain certain missing energy in nuclear beta decay. We are not going to talk about this today. It's a topic all in itself. So the next particles after that, the 32 that were detected were muon and pion. So in the next 10 years, two new particles were detected in cosmic rays. One was muon, its mass was 106 MeV, and the other was called pion, its mass was 140 MeV. And at this point, one must ask, what do I mean by writing mass in MeV? MeV is mega electron volt, and it is obviously a unit of energy. So why do I call it MeV? It is standard practice in particle physics to express masses in MeV, in units of MeV. Actually, it means MeV over c square. From the mass energy relation, you can see that M is E over c square. But we are, for convenience, we just put c equal to 1 everywhere and write mass unit also as MeV. So the particles that were discovered were by 1947 increased by two numbers. However, in the next 10 years or so, hundreds of new particles were seen. And these particles were seen first in cosmic ray experiments and then in the lab also. So we'll just read out the names slowly of these particles. We have the electron, the positron, the proton, neutron, and photon, muon, neutrino, and pion, which we have already discussed. Then the new particles that were seen were given names like rho, meson, kaon, K, lambda. Then the next is eta. Then the next is omega. Then the next is called sigma. Sigma came in 3 charge varieties. Then the next is called cascade, and so on. And it went on and on. I mean, so much so that people they ran out of names. And so they started putting stars. So there was then sigma star, and then there was the cascade star, and so eta and eta prime, and so on. At the same time, around that time, 1950s, the particle accelerators were built and people started producing particles at the lab also. Apart from cosmic rays, one could bombard, for example, protons with pions and create new particles. So one such particle was lambda delta resonance, which came in 4 charge varieties. So each of these newly discovered particles was assigned as a property called strangeness. I don't have the time to go over it. But basically, the particles had a funny behavior that they behave differently while being produced and differently while decaying, and therefore they are called strange particles. And analyzing their production with what they are being produced, etc., what are the interaction times of production, etc., they were assigned a certain property called strangeness, which is going to play a certain role in our story very soon. The question at that time was, are all these particles elementary? Can there be hundreds of particles as elementary particles? Definitely no. So what do you do in that case? What you do is you try to look for patterns. Okay? Just like periodic table, if you analyze the periodic table, you see certain repetition of properties, and that gave the indication that there should be a certain atomic structure. Okay? So similarly, one tried to classify the particles. There were different ways. One of them was on the basis of interaction. So let us slowly absorb this. Particles which take part in strong interactions. Strong interaction is the one which is the strongest, okay? The nuclear force. So the particles which take part in strong interactions, they're called hadrons. So these were particles like proton, neutron, pion. Then there was lambda, K, etc. And all the particles which do not take part in strong interactions are called non-hadrons. These are particles like electron, muon, neutrino, and so on. So this is the classification based on the interaction. So after dividing them into hadrons, that is strongly interacting particles, and non-hadrons, strongly interacting particles, they were further classified on the basis of their spin. So we all know that electrons and protons have spin half. The elementary particles that were detected were also having different spins. So you could produce particles with spin half, spin 3/2, spin 0, spin 1, and so on. So all the hadrons which had half integral spin were called baryons, like proton, neutron, delta, lambda, cascade, etc. And all the particles which had integral spin like 0, 1, etc. were called mesons. These were examples were pions and kaons. Non-hadrons, of course, are particles like electron, positron, muon, neutrino, and the force particles, photon, W, Z. We are not going to be concerned with the right part of this picture. Another classification was done on the basis of a property which is called isospin. So this was an effort to reduce the number of elementary particles. So we know that proton and neutrons are very similar in their behavior as far as strong interaction is concerned. They just differ in their charges. So one can group them together into one particle and say that they are different states of the same particle called nucleon. Just like an electron can be in spin up state or spin down state. So you can treat spin up and spin down states as two different electrons, or you can treat them as different states of the same electron. In the same way, nucleon has isospin of half, and therefore it can be either in isospin up state or isospin down state. When it is in spin up state, we call it proton. When it is in spin down state, we call it neutron. So this reduces the number of nucleons from 2 to 1. The same way, the 3 pions, they are similar in every way except that they have different charges and slight mass differences. So the 3 pions were said to be forming a isospin triplet, which means they were assigned an isospin of 1. And if isospin is I, then the number of particles in the multiplex is 2i plus 1. So there were 3 of them. Similarly, so all these particles could be put into groups of 2, 3, or 4, or 1. Okay, so it's called isospin singlet, isospin doublet, isospin triplet, isospin quartet, and so on. So that reduces the number of particles to some extent. After that, Gell-Mann and Zweig, they went further and they expanded this idea of isospin categorization on the basis of isospin to include strangeness also. What they did was they grouped particles on the basis of their isospin, up or down position, and strangeness. So in these pictures that you see, we are plotting the strangeness of particles on the y-axis and the isospin third component on the x-axis. And when you do that, for example, K plus and K minus form a doublet. So there are just 2 particles in that line, the top line on the first figure. Similarly, proton and neutron form an isospin doublet. So there are only 2 particles in the top line. The second line has, in the figure on right, has a sigma minus, sigma naught, and sigma plus, which means they form a triplet. Okay. So on the x-axis, I am plotting all the particles in the same multiplet, isospin multiplet, and on the y-axis, I am plotting the strangeness. What was curious was that when one did that, the 8 lightest mesons. Remember, mesons are the integral spin strongly interacting particles. Okay? So the mesons, 8 lightest mesons are 3 pions and 4 kaons, and in eta and E prime. So all these were forming a hexagonal pattern with 6 particles on the sides and 2 in the center. This was called 8-fold way. Similarly, the 8 lightest baryon, the figure on the right, the baryons are particles like proton and neutron, which have half integral spin. So the 8 lightest particles, which are proton, neutron, the 3 sigmas, lambda, and the 2 cascade particles, they also form a similar pattern. But it was not just that, all the particles, it was not just the 8 lightest mesons and 8 lightest baryons, but all the particles could be put into arrangements of this kind. All of them either form a pattern containing 8 particles, 1 particles, or 10 particles. Okay. So that indicated that there must be something, there is something going on which is enabling us to categorize particles into these beautiful pictures. So I want to start thinking about what are these diagrams. So Gell-Mann and Niemann looked at this question, and they asked the question, they tried understanding these diagrams, and they realized that these diagrams are something very similar to what we find in a branch of mathematics called group theory. By the way, since I'm talking to computer science students, I just want to mention that Niemann was an engineering student. He did his bachelor's in engineering, and after that he did his PhD in particle physics. And within a year, he proposed this model. So what they realized was that these diagrams are similar to objects in group theory, which are called 8-dimensional representations of group SU3. Now, don't expect to follow, or if you don't know any group theory, don't try to understand this word. Just take home this message that the 8-dimensional representations of group SU3 in mathematics can also be plotted in a similar way, and the plots are exactly identical to what we were seeing in the elementary particle spectrum. How does it help that? It helps us because the objects in mathematics, that is the representations, they can be constructed by starting with one of the smallest representations. So SU3 we have seen it must be having a 1-dimensional representation, 8-dimensional representation, 10-dimensional representation at least, because we are saying that our diagrams are exactly the same as those. But all these higher dimensional representations could be constructed by starting with a simplest representation, which is called a fundamental representation. Just like you take any example in mathematics, if you have the number 1 and if you know how to add numbers, you can make number 2, number 3, number 4 just by adding. So similarly, the representation, fundamental representations of SU3 can be added in a way to create the 8-dimensional and 10-dimensional representation. So the question that they asked was, where are the particles which belong to the fundamental representation? And so one needs to know what does the fundamental representation looks like. It appears that the fundamental representation is 3-dimensional and it looks like a triangle diagram. And that was the beginning of the idea of quark. The question is, are there any particles in nature which belong to this representation called the triplet? And there was nothing. So this was, so they proposed, Gell-Mann and Niemann, they proposed this quark hypothesis, which said that there are 3 fundamental particles called the U, D, and S quark. The quark name was just given, there's a certain mystery to that, but basically in German it means junk or something like that. So Gell-Mann was till the end, till very late, was not convinced that they are actual particles. He thought they are mathematical objects which are fitting my theory. So he proposed this name quark. He said there are 3 quarks which belong to, which we don't see in nature, but they make up all the other particles, because by combining these quarks, I can construct the higher dimensional representations. So this is the picture of what the 3-dimensional representations of SU3 look like. And you can just superimpose these triangles one over the other and create the 8-dimensional and 10-dimensional pictures. So there are 3 of them. U and D quark were given the charges plus 2/3, and the S quark was given the charge minus 1/3. Correspondingly, there are 3 anti-quarks. U bar and D bar were given the opposite charges, minus 2/3 and minus 1/3, and S bar was given charge plus 1/3. So U has charge plus 2/3 and D and S have charge minus 1/3. So in terms of these, what they suggested, the quark model, they proposed the quark model, which said that all the regularities in this particle spectrum can be explained by assuming that all the baryons, that is the half-integral particles, are made up of 3 quarks, which are called up, down, and strange. All the mesons are made up of 1 quark and 1 antiquark. And U and D are isospin doublet, just like proton and neutron, and S is a isospin singlet. So these are some pictures of some of the hadrons. For example, you have the particle written P is the proton, which is made up of 2 U and 1 D quark. And you can add the charges and check that it is charged plus 1. Similarly, you have this lambda in the front, which is a U, D, and S. Okay. Sigma plus is 2 U's and 1 S. So one could superimpose the quark and antiquark multiplets and recreate these diagrams and then identify the quark content of each of the particles. Okay. And this is how the assignment, even if you don't know the pictures, you can just assign the charges plus 2/3 to U and minus 1/3 to D and S and construct the charges of all the known particles. So this is a picture of what is called the Baryon Decublet. I told you that there were also 10-dimensional representations which look like this big triangle. In the first line are the 4 deltas, which we talked about earlier. Second line is resonances of sigmas. So I had 3 sigmas in the proton neutron octet diagram, and these are the excited states of those cascades and so on. And each of these could be assigned the quark structure as given in the table. And from the quark structure, one could predict their charges, their strangeness, and so on. Another thing that was found from this diagram was that there was a definite pattern in the masses. So the particles in the top line are the lightest, second line are little heavier, third line are still heavier, and the fourth line, the last line, has a particle called omega minus, which was not known at that time. So by looking at these mass patterns, Gell-Mann predicted that there should be a particle called omega minus with charge minus 1, which should have strangeness -3. So now strangeness -3 means that it is made up of 3 strange quarks. The reason for this mass increase is that strange quark is a little heavier than mu and d quarks, and therefore, as you go down the strangeness line, the masses increase. Omega minus was the prediction, and soon after this particle was found again in the lab, and that was the first success of quark model. However, even then, many people did not believe in the quarks because they were not seen in physics. Unless you see something in the lab, no matter how beautiful your theory is, it's useless. One of the problems that came with the quark model was because of the particles in this decuplet which are in the corner. So if you look at the corner, there is a delta plus plus which has 3 U quarks. There is a delta minus at the other corner which has 3 D quarks, and the bottom, of course, is omega minus, which is 3 S quarks. These are all particles with spin 3/2, and therefore their spins can be oriented in the same direction. So a delta plus plus can be in a state in which all the 3 quarks spins are pointing upwards. Similarly, delta minus can have 3 Ds in the same state, and omega minus can have 3 S's in the same state. Now this clashed with what is called Pauli explosion principle. So you must know this when you start filling the atomic levels, you cannot put 2 identical electrons in the same state. So this configuration that I'm seeing here, U up, U up, U up, indicated that I have 3 fermions, because quarks are spin half particles, which are all in the identical state, which was not allowed by Pauli explosion principle, and people started looking for a solution to this problem. Several solutions were proposed, and it was Greenberg who suggested that we can explain this existence of, so according to Pauli exclusion principle, delta plus plus should not exist because it has 3 fermions in the same state. So he suggested that we can allow this. It is possible if we allow the quarks to carry another quantum number, which is different for all the 3 quarks. Okay. So he said that there should be some charge. He called it color charge, which should be different for all the 3 U's in the delta plus plus. This is just like the electric charge. This electric charge comes in 2 varieties. Here 2 varieties they're not going to work. If I assign these charges plus and minus, then again in the system of 3 quarks, 2 of them are going to have identical quantum numbers. So this color charge had to come in 3 varieties, and they were given the names red, blue, and green. This red, blue, and green has nothing to do with the actual color as we see in everyday life. This was just a name given to the new physical quantity, that is the color charge. So the 3 quarks in baryons, like proton, neutron, and lambda, they should be carry different color charges. That was the color hypothesis. And the wave function then, if you know a little bit of quantum mechanics, the wave function of this particle then becomes antisymmetric in the color degree of freedom. However, electric charge, which is the charge of the electromagnetism, is observable in the lab. You can measure the charge of a charged particle. In this case, I did not have access to the quarks. I could not see them, and therefore I cannot measure their color charges, and there were no particles in nature also which were carrying any color charge. Okay, so to save this idea of quark model, people propose that the physical particles always appear in colorless combinations. Okay? So when a particle is made up of 3 quarks, colorless means equal amount of each of the charges. So the color state of the baryon will be equal amount of R, B, and G. And this long expression I have written to show that even if you rotate among R, B, and G, if you interchange R, B, and G, this thing will change sign, which is what is required by the Pauli exclusion principle, that the wave function should be antisymmetric under interchange of 2 identical particles. Similarly, for the mesons, remember, consist of a quark and an antiquark. An antiquark has all the quantum number opposite to the quantum numbers of the quark, and therefore there was the concept of anticolor also. So there are 3 colors R, B, and G, and there are 3 anticolors R bar, B bar, and G bar, and mesons are colorless combination of these. So now we have the picture that we drew of the hadrons of the baryons is changed in the sense that they are all made up of 3 quarks, but each of the quarks should be carrying a different color. The thing to note is that the hadrons do not carry any net color charge. They are color neutral, in the sense they carry equal amount of all the charges. Similarly, the mesons carry equal amount of the color charge and the anti-color charge. Now, the $1 million question there was, okay, fine, everything is fitting so well. We are predicting omega minus. We are able to identify all the particles as multiplets of this group SU3. But where are these quarks? We should be able to isolate them and we should be able to see them. Now, to say that this hypothesis of quark confinement was proposed, that the quarks are absolutely confined within the hadrons. They are very tightly bound by a very strong force to each other. And if you try to separate them, if you try to break apart the proton and try to take out the U and D quarks, the force between them increases. It increases to such an amount that finally the proton breaks up and a lot of new quark anti-quarks come out, and you instead of getting the U and D quark, you start getting new hadrons. So quarks can be only found in bound states. And what keeps them together are what are called the gluons, or the exchange particle of strong interaction. So why don't we see them? So this is a picture of why we don't see the quarks. This is a bound state on the left, number 6, is the bound state of the 4th quark, which was seen later after quark model was proposed, after QCD came up, which is called CC bar bound state. J upside is a neutral particle, charm and anti-charm. If you try to separate them, the interaction energy between them increases so much that new quark anti-quark starts popping up from the vacuum out of nothing. And then these new pairs also move in the same direction in which the original C and C bar are moving. And then as the distance increases, force increases between them, and they again start forming bound states. So instead of getting C and C bar, here you are getting a bound state of a C and D bar and C bar and D, which are called D plus and D minus. If you try to break a hadron, you create more hadrons. So you cannot see any colored particles. So quark model could explain the existence of all the hundreds of these baryons and mesons. However, one needed to see the one needed to have an experimental evidence, and that came in 1968-69 in the famous experiments performed at Stanford Linear Accelerator Center. These are the famous deep inelastic scattering experiments. What happened in these, what you do in these experiments is you bombard a proton target with an electron beam, a very high energy electron beam. And you can see in this picture called the Finemen diagram that the electron and the proton, I have drawn the proton as a bunch of lines. So these lines are the quarks. So this electron interacts with the proton and scatters, and then the proton breaks up. And instead of instead of getting the proton, you get some lot of unknown states. However, you don't need to look at those unknown states. You can find out what is the nature of this target, this green target that you are hitting with the electron beam, just by looking at the spectrum of the scattered electron, that is EK prime. So if this target was a point target, you will expect to see one kind of a spectrum. If it is an extended target, you would expect to see another kind of a spectrum. And if it is a target consisting of point targets inside, then you expect to see a third kind of a spectrum. Just take analogy with the Rutherford backscattering experiment. If it is Thomson model is correct, then you expect to see one kind of spectrum of the scattered particle. If it is if the nucleus is contained in the center, then you expect another kind of. Same way, you can predict what kind of spectrum you will see of the scattered electron if the target, the green object, has a certain nature. It is point, it is extended, or it is made up of point charges. And this is what was concluded from these experiments, that inside the proton, there must be 3 lumps of charges. So all the masses located at 3 lumps, and the scattering appeared as if it is taking place through these 3 lumps. There's a very detailed analysis of this kind of thing, which establishes the fact that the proton is made up of 3 point-like objects, and they were called the partons at that time because people were still not ready to accept that quark model is correct. So this is actually called the quark parton model. So these were actually the quarks that were proposed earlier. There's another question that came up, that are there only 3 quarks? And it was by that time the theory of weak interaction was also maturing. A lot of developments were taking. This was very exciting times, the 60s and 70s. They're very exciting time for particle physics, and it was felt that there were certain decays which were allowed by the quark model, but which were not taking place. And one of the solutions to this fact was to propose a 4th quark. And these people, Glasgow, Leopolis, and Miami, they suggested that you can, if there is a 4th quark, then we can explain this. So the idea of the 4th quark was already there. And in 1974, at Brookhaven National Lab, this 4th quark was seen in the form of a resonance of a new particle. So a new particle was seen, which could not be identified with any of the bound states of quarks and antiquarks. And so therefore the idea of a 4th quark, charm quark, was proposed. And the number of quarks increased from 2 to 4. And these were put into 2 generations. So UD were called the first generation. These are the quarks which make up proton, neutron, all of us, all our bodies, everything in the that we see all around us. And then C and S are the higher, heavier quarks. They were partnered into what is called 2nd generation. And immediately after that, a 5th quark was seen again in the lab. Okay? So this is a case where something was seen which was not even predicted. However, we were suspecting that there should be a 3rd generation, because there were 3 generations of leptons, that is particles like electrons. We'll not go into that. But this picture on the bottom is what you see when you discover a new particle. So you have a continuum, and in between you see a bump. And this bump is at a certain energy, which tells you that a particle of such and such mass has been created. So this new bump could not be explained in terms of the known quarks, and it was interpreted as the bound state of a new quark, which is called the bottom quark, and its antiparticle. So now we had 2 generations and 1 more particle. Therefore, people expected that there will be a 6th quark also to complete the 3rd generation, and that was the famous top quark, which was finally seen in 1995. Okay, we will not go into how these things were discovered because of lack of time. Let me now go to where all this fits in the standard model. So the standard model, as you see here, is the part. This is the particle content of the standard model. So the particles in red are the quarks and antiquarks, and the second particle in the green column is the gluon, which are actually 8 in number. These are the characters of our story today. The rest of the particle, leptons in blue, in yellow, and the other 3 green intermediate particles were also discovered during all this during this journey of particle physics. We are not going to do that today. The other thing that is important for us, our story today, is the Finemen diagram in the center, which shows that all the metal fields interact through exchange of force field. This is the essence of the modern theory of particle physics. There was another character in the story which was very essential, that is the Higgs boson, and that was also discovered in 2012. And the discovery of that, the standard model was complete. However, today we are talking about the theory of color. So we have seen that the eightfold way arranged the particles into these hexagonal patterns, and they were identified as the representations of the group SU3. Particles in the same representation are similar, and they would have identical masses if this SU3 symmetry, the theory has a symmetry which is an exact symmetry. In the case of eightfold way, the particles were not having same masses, and you said that the symmetry is a broken symmetry. In 1971, Fritz and Gell-Mann proposed that there is another SU3 symmetry in the theory of quarks, in the theory of strong interactions, which was called the SU3 of color, which means that the 3 quarks that we have identified, the red, blue, and green quark, also form a triangular pattern like this, which means that they belong to the fundamental representation of a group SU3. This is not the same group SU3 which was forming the baryons and mesons. This is a new SU3 in which the states are, the fundamental states are the color states. And then again, we can do the same exercise and combine this triangle and the inverted triangle and construct the hexagon, as you can see in this picture, the right. So you just superimpose the inverted triangle on each of the red, green, and blue dots on the inverted triangle, and you will be able to form the hexagonal pattern. What it shows is that a 3 representation and 3 star representation combined to give an 8 representation and a 1 representation. However, we know that the physical particles are all color neutral. So in this case, only one-dimensional representations exist in nature as the free particle, as the physical particles. Okay. So what the theory of SU3 of color says is that each quartz has one of the 3 color charges, which are denoted here with green, red, green, and blue. And then each antiquark has 3 complementary color charges, which are shown as anti-red, anti-green, anti-blue in the picture. And then the new thing that comes here is that the gluons themselves are colored objects. This is unlike quantum electrodynamics. Why don't we see the color charge in nature? Because of the confinement. That is, quarks are always absolutely confined inside the hadron. As you see in the picture, if you try to separate the quarks inside the hadron, then they just so much potential energy is created that new quark-antiquark pairs are created, and then they go and form pairs with the original quarks, and they give rise to new particles. So we cannot see the quarks. So how do we check whether color actually exists? Okay. So this experimental evidence for color came indirectly from certain processes. I'll not go into detail of this. In very short, this particular diagram, which shows decay of a pi naught into 2 photons, this is a Finemen diagram, has a triangle in the middle, which shows which loop is because of a quark going in the loop. So the probability for this process to occur is going to depend on how many varieties of quarks are present. If I have 3 quarks, I have to calculate this number corresponding to this diagram for the U quark going around, for the D quark going around, for the S quark going around, add them, and then that will give me a number which can be compared with the experiment. It was found that unless I assume that quark comes in 3 colors, I cannot explain, I cannot have agreement with the experimental number. Similarly, this is another process. We don't have time to go into all this. I think I'm running out of time. But basically, in this also, there is you construct an observable. In this case, it is the ratio of cross sections for electron positron giving hadrons to cross section of electron positron giving a mu plus mu minus pair. Both of them can be calculated, and it so turns out that at high energies, this ratio depends only on the charges of the quarks and the number of quarks. And again, one found that unless I have this NC, which is the number of colors in my theory, unless I put NC equal to 3, I cannot match the theoretical value with the experimental value. These are indirect evidences in favor of colors. Based on these, Finemen and Gell-Mann constructed their theory of quantum chromodynamics, which is called the gauge theory of color. Gauge theories are a special kind of theories. Basically, as we have said so many times, the essence of them is that the force is mediated through exchange of particles. Quantum electrodynamics is the gauge theory of electromagnetic force. Photon is the mediator. Similarly, quantum chromodynamics is the theory of nuclear interactions in which the mediator is the gluon. The difference between QD and QCD, QD is electrodynamics, CD is chromodynamics. The difference between them is that the exchange particle of electrodynamics is neutral. Photon does not carry an electric charge, but the mediator of strong interactions, that is the gluon, is a bicolored object. It carries away the color of the incoming quark and it brings in the color of the outgoing quark. So you can see that you have a UV coming in, giving away a bicolored GBR and turning into a UR. So these are also some pictures which show how the color of the quark changes when it emits a gluon. And the other difference between the two is that the strength which the electromagnetic force couples to the charged particles is much smaller as compared to the strength of the strong force. And also this coupling changes with distance in a different way. We have seen that if we try to separate the quarks, the force between them increases. So in case of electrodynamics, the force decreases with distance, but in case of chromodynamics, the color force becomes stronger and stronger when you try to separate the quark. And at very short distances, the quarks move almost freely. So now this is the picture of a proton. Earlier we showed the proton as made up of 3 quarks of different colors, but in fact, inside the proton, there is a very dynamic environment. There are a lot of gluons continuously being exchanged, created. These gluons can create new quark-antiquark pairs, which again recombine. So the proton is actually made up of just 3, not just 3 main quarks, but also gluons and pairs. And this is about how do we see the gluons. I'll just skip this. So we come to towards the end. So what is the role of quantum chromodynamics in collider physics? It's a very good theory, just like electrodynamics, it tells me how to calculate the quantities for quark scattering, quark-antiquark scattering, etc. But I don't see them. What I see in the lab are the composite states, the bound states. So what I'm measuring is in the lab is the cross-section for the process AB to CD. I'm looking at AB and CD, but what I'm calculating in QCD is for the quarks and antiquarks. So how do we connect these two? How does QCD help me in that? So it does that in terms of what are called factorization theorems. I'll not go into the details of this. Basically, the left-hand side is a quantity, hadronic quantity, which is being measured in the lab. And on the right-hand side, I have a similar quantity for small a and small b, which is being calculated by quantum chromodynamics. And the two are connected by this theorem, which also requires some certain inputs, which are these functions F called pattern distribution functions, which give us the probability that I will find a small a quark inside a capital A hadron. And this is represented here pictorially. So all these experiments that we are doing at Large Hadron Collider, whether to detect the Higgs boson or to look for new particles, they involve collision of protons. And therefore, I will need these functions. If I want to calculate the cross sections, I need to calculate, I will need the quantities involving quarks, which are calculated through my theory quantum chromodynamics. Why do we study? What is the need to study QCD after so many years? If it is established, it is successful, it is a very elegant theory. There are several reasons. I'll just go into some of them. One of them is that we need to know the parameters of quantum chromodynamics very accurately so that I can make predictions. Similarly, we need to know the pattern distribution function. There is a whole field of quantum chromodynamics devoted to that. I need to determine the pattern distribution functions because I'm going to use them in my calculations of physical quantities. And unless they are accurate, I will not be able to get accurate results. When I'm looking for new physics, that is for particles which are beyond the standard model particles, then I need to first clear the background. I need to first figure out what is coming from the standard model. And for that, I will need quantum chromodynamics calculations very accurately. And therefore, one is always trying to make our chromodynamic calculations more and more accurate. This is an area on which I work. And then finally, we understand the strong interactions at very short distances. Perturbative QCD is a very successful theory. But
Professor Mishra, we have 5 minutes more.
I'm just stopping. I'll take just 2 minutes more.
Okay.
If we go to large distances, then there are phenomena like confinement. How do the hadrons form from the quarks? All these things are still not understood. And these are areas which are focus of very active research right now. So I'll just summarize what I told today. Quantum chromodynamics is an important component of the standard model of particle physics, which I tried to explain in short. The quark model, which was initially proposed, describes the hadrons, which are particles like protons and neutrons, as bound state of more fundamental objects called quarks and antiquarks. And these quarks and antiquarks are bound together with the help of gluons, which are the glue or the binding particles. Quark hypothesis was initially proposed on the basis of symmetry patterns with analogy from group theory and purely theoretical reasons, but now it has been validated at the experiments, and there are more ways also which I did not go into. And it provides a beautiful and correct mathematical description of the strong force between quarks, and it provides us a tool for calculating physical quantities which are being measured at hadron colliders. And finally, QCD will continue to play an important role in high energy physics because we need to cut out the QCD background to look at the new physics. And apart from short distance phenomena, there are large distance phenomena and also QCD under extreme conditions, which I did not talk about, which are also currently a very active area of research. So thank you very much. And this is a picture of the Large Hadron Collider. So I thank you very much. And I would be happy to take some questions from the students.
Thank you, Professor Anuradha. Mr. is a nice and elaborative talk. So I can hand over Dr. Kalpana Patel to initiate the questions. So the questions are, some of questions are in the chat box and some of the questions are available in the YouTube. Maybe Dr. Kalpana can handle the questions, which is, yeah.
Sir, I cannot see any question because the direct message of the question is to ma'am only.
Okay, okay. So then okay, then
yeah, I'll read it out. The question is, what is the significance of quarks at large scales, larger scales than modern computers? This is by Kinchuk Goel. It's a direct message. So significance of quarks at larger scales is that at larger scales, they form the hadrons, and therefore, if we want to study the behavior of hadrons, we need to know how they behave at larger scales. And modern computers, I don't understand these questions. Right now we are not using particle physics in computers, but we do use a lot of computation in particle physics. So the data that comes from, for example, jet analysis, it requires a lot of computer science. So, for example, I talked about grid computing. So you need very sophisticated computers to analyze the data that comes from particle physics. But how it can change the computers? I don't know. It may happen in future, not right now.
There is a question from the Shreya. How is quantum electrodynamics is different from the quantum chromodynamics?
Yeah, so I talked about several differences. The first thing is that the charge of the particles which interact through electrodynamics can be either in two varieties, plus or minus. Whereas the charge of the particles which interact in chromodynamics comes in three varieties, R, B, and G. The second difference is that in quantum electrodynamics, the charge, the particle which is causing the force, that intermediate particle, photon, is neutral. It does not carry the charge, electric charge. But in quantum chromodynamics, the gluons themselves are charged particles. And there is this concept of bicolor. So they are not just charged, they are bi-charged. So they carry one unit of charge, and one unit of color charge, and one unit of anti-color charge. And they are different units. They are not neutral.
Okay, there's a question from Tejashi. What is the role of QED in the classical mechanics?
QED is the quantum theory of electrodynamics.
Is asking what is the role of classical mechanics?
In classical mechanics, classical physics is different from quantum physics, but in the large distance approximation, quantum physics should give you the results of classical mechanics. So quantum physics is more general, classical physics is restricted region, and there is no role. I mean, when you are at short distances, you have to use quantum physics. When you are at large distances, you can use quantum physics or classical physics. It doesn't matter. That's an approximation.
There's a question from the Shivangi. The baryons and mesons have which kinds of interaction to show their characteristics? Baryons and the mesons. Baryons and the mesons. have which kinds of interaction to show their characteristics?
So baryons and mesons can take part in all interactions. They can take part in strong interaction. We have discussed that. They also carry charge, so they can take part in electromagnetic interaction, and they also take part in weak interactions. But you can find out which when they are behaving in which way by looking at the strength of the interaction. So there is a typical time scale associated with the process, scattering process, or there is a, just as there is a lifetime associated with the decay process. By measuring that, you can find out in this particular reaction which interaction through which interaction the particle has participated. So the proton, for example, proton takes part in neutron decay, which is a weak interaction, and it also takes place. It also takes part in proton-proton collision, where a strong interaction takes place. It also takes place in electron-proton scattering, where electromagnetic force is working. So baryons and mesons can take part in any interaction. There are a couple of questions on the in private chat. So can I first answer those? Yeah.
Yeah, maybe you can. Yeah.
Yeah.
Because
so
we have a limited time because we have to close at.
I think I should first answer the Zoom audience.
Yeah.
So Anushka is asking, what is quantum color? So it's a color quantum number. What we are talking about? So color, we are not talking about, when you say color here, we are not talking about the usual colors like red that I'm wearing or anything like that. It is just a name given to a charge associated with strong interaction. And it's called color quantum number. So to each quark, you can assign a particular quantum number which takes 3 values, R, B, and G. That is called the color quantum number. Then there are a couple of questions from Kinshuk Goel. He's asking, do quarks make up electrons just as they do for protons and neutrons? The answer is no. Electrons are elementary particles. They are different kind of particles. They are not made up of quarks. They are not hadrons. They don't take part in strong interactions. They are called leptons. And the second is, can mesons be created artificially just as they exist in nature? Also, what makes up these quarks? Is there something even more fundamental? Yes, they can be created artificially. You can they are produced in the lab actually in these collision experiments also. And what make up the quarks? We don't know. We believe that quarks are fundamental particles so far.
Maybe we are just running out of time. I think we have to stop here. There's a lot of questions, obviously, we cannot answer at this moment. So maybe if the time permits, I mean, say if she, Professor Anuradha, if you can just write them, then it will be nice in the letter. So therefore, now I just hand over the mic to Dr. Kalpana. Dr. Kalpana, please.
Thank you, sir. I would like to say a vote of thanks if Vanna ma'am permit me.
Yes, you can, yeah.
Okay,
yes.
Okay. So thank you, Professor Anuradha Mishra, for your valuable and informative lecture on quantum chromodynamics. And my special thanks and sincere thanks goes to Professor Vanna Nanal ma'am also, and Professor Samit Mandal sir for their cooperation and support and timely guidance for the conduction of this expert lecture. My regardful thanks goes to our Dean Campus of Life, Professor Naveen Elawat sir, Dean of Academics, Dr. D.K. Sharma sir, Professor D.K. Sharma sir, Dean of Admissions, Professor R.P. Mahapatra sir, and our Deputy Registrar sir.
Hello. Yeah. Yes.
Involved. Yes. And my last thanks, at last, my also goes to all the peoples involved in making this event, or we can say expert lecture, to be successful, who are in presence and in absentia both. Thank you, IPA. Thank you, DAE. Thank you, CBS. Thank you for your support and guidance. Thank you.
Okay, thank you, Professor Anuradha Mishra, and thank you, Kalpana. Dr. Kalpana Patel. Also thanks to everybody who actually participates and attend the meetings, attend this nice lecture. So from my side, so I just now thanks everybody and conclude, and now we can close the session. Okay, thanks everybody again, and good afternoon.
Thank you, sir. Good afternoon.
Okay, I just end the meeting.